Welcome to this webinar in the Iliad webinar series, Iliad hackathon webinar series. Today we are going to address sensors, and we will get an overview of the Iliad sensors. There's plenty, and we will also dive deeper into and look closer to one of the types of data, sensors that we have, namely drifters. My name is Bente Liljaby. I'm going to be your host. I encourage you to write questions and comment in the chat, and we will be able to give you the floor in the Q&A session for sure. And if there are some burning questions that you will need for clarification, just raise your hand and we might give you the floor in between if we see that fitting. I'm just saying that we are flexible with that, but we do really want you to engage with us and ask questions. This is the way we learn what is interesting for you, and you will learn from our excellent speakers. So before we start with the program, I will also introduce Iliad a little bit. Not every one of you, even though several knows about Iliad and digital twins already. I think we can, warm up with some introduction to Iliad. So let me share my screen. And now I'm on a computer that is this. You should see the program. So sensors and digital twins of the ocean is what we are talking about today. I will introduce Iliad first. We get an overview of sensors by Georgios Zelaios, and then the Wavy drifters will be detailed more by Marco Oliveira. And then we have the Q&A. So just a quick reminder what the digital twin of the ocean, what we mean by that. It's simply said, it's a virtual representation of the real world. And it provides us with information about what now and also what next, and we can play with what if scenarios. In Iliad, we are appreciating the wealth of different types of data describing a digital twin of the ocean. So we are also looking at data from the past, and we are also incorporating data around the digital twin, so it could be statistics or economic information, etc. So we try to, in Iliad, we are defining the digital twin of the ocean as a very broad description of a specific thematic twin or a local twin. So Iliad in the seashell is thus we are enabling an ecosystem of interoperable digital twins for the ocean, and through using existing resources. There are multiple resources existing already, infrastructures, data repositories, etc. And we add sensors data, and this is what we are addressing today, the additional data that we collect via sensors. And of course, we do have a focus also on citizen science. All of this will be made available or are being made available on the Iliad Marketplace, where you will find the digital twins, thematic and local, but also its components and other material related to building digital twins. All in all, we are providing solutions or contributing to solutions addressing societal issues. Iliad address or appreciate that the ocean is vast and very complex, consisting of different components, biological, geophysical, and also the interaction between all of these components, specifically the human interactions and human activities. As I said, we are enabling resources from the ecosystem around digital twins, and there are so many resources, not only in Europe, but it's a European project, but we do have partners also from Africa and the Middle East, and we are enabling the interoperability of all of these resources, so alignment using standards and best practices is very important for Iliad. As I said, we are talking about multiple twins, and they are representing different thematic areas. You see here with 12 categories that we have divided our twins in, and they have ranging from fisheries to oil spill, to insurance, plastic pollution, etc. You see the whole panel of thematic twins here. And of course, the twins are placed locally, so we are also addressing very local twins. Here is a quick overview of the logical architecture of Iliad, and you see that on the left-hand side, that's where we have sensors and different data sources, and we follow then the data pipeline where we are preparing and harmonizing the data. We are storing the data, and we are then doing analysis on the data, providing applications and services that are presented and visualized in various ways depending on the needs of the end user. And so it's a large variety of solutions, but based on the same structure architecture. And here you see the twins, a series of twins, the thematic and local twins are reusing, we are trying to, we are facilitating the reusability of several of the components so that they are as interoperable as possible, and that we are economically using the resources. So it's an efficient way of using all the different types of resources going into a digital twin of the ocean. And finally, this is the last slide I will share with you now. It's an overview of the Iliad project. We are around 56 partners, representing partners from industry, academia, NGOs, and from Europe, Africa, and the Middle East. So it's a very diverse group of partners. The funding is around 19 million euros in total, the ballpark from the European Commission. And the project is 3 years duration, and we just got the prolongations, 3.5 it was, but now it's 4. So we are in the last year of this project. So with that, now I think I'm very excited that we can go and get an overview of the sensors. Professor Georgios Alaios from the Democratic University in Greece, he's responsible for sensors. He's a very experienced oceanographer. So Georgios, the floor is yours.
Thank you, Bede. Good day all. I'm Georgios Alaios from the Demokritos University of Thrace. I hope you can see my screen. So I will guide you through the sensors of Iliad and give you some ideas on how to integrate sensors in digital twins, especially digital twins of the ocean. Just a very quick, brief overview of how the sensors fit in a digital twin. As you can see, the digital twins are the new ideas that we have now in the framework of Industry 4. And we have the physical and the digital space in a digital twin. And what we are trying to do is to interrelate these two spaces. And to do that, to move from the physical to the digital ocean or to the digital world, what we need to have the sensors. We need a lot of sensors, in fact. We need models. All these sensors and models will create big data and will be stored in cloud systems and will be utilized by machine learning and AI algorithms. And when we do that, we have efficiently crossed the line where we, in fact, are transferred from the physical space to the digital space. And then we need to go back from the digital to the physical space through a series of operations, of controls, optimizations of the system, diagnosis of any problems, and decision support systems that really optimize the operation of the physical system. So this is how the digital twin is developed in Iliad. And as Bende explained, there are a series of pilots which in fact formulate independent digital twins. And these pilots cover different marine and maritime activities, as you can see, the offshore wind energy farms, the tidal, or the oil spills and the fisheries. So we have divided the digital twins in two classes. One is the marine environmental ecological digital twins, where we only move from the physical to the digital world using all these tools that I explained earlier. And this refers to systems that we cannot really control and optimize easily because they are environmental systems like the marine litter or the jellyfish or metocean conditions or the ballast water or any pollutants in the sea. And then we have a good example of that is the oil spill digital twin that is developed by DUTH, by Democritus University of Thrace, for Thracian Sea. I will say a few words later on, and I will show you the sensors we are using for this digital twin. And then we have the two-way digital twins, which are complete digital twins, engineering, industrial, maritime digital twins, where we make the full loop. We move from physical to digital space, and then we go back. Like, for example, anything related to marine renewables or to fisheries or to ports, safety, etc. And a good example is this one, where we have a wave energy converter, which utilizes the energy from the waves. And there is a pressure accumulator over here, and based on the pressure which is exerted, we are able to rotate this hydraulic motor by which we are producing energy, and the energy is stored at the end of the loop. So what we need, of course, is to provide to the developers of the system the offshore winds, the offshore waves, the transformation of the waves, the nearshore waves, and then a series of sensors near the wave energy converter and a series of models for the forecast, so that they are able really to optimize the layout, to optimize any operational decision making, to prevent mechanical damage, especially under conditions of extreme waves, to prevent the corrosion alert. All these are extremely important for the wave energy digital twin. So overall, this is the pipeline that we have in Iliad in almost all of our pilots. We have the sensors, we have the models for the forecasts, we have the AI algorithms, then we have the utilization of existing resources like satellites and external databases, the citizen science, and all these are led to a platform formulating a constellation of digital twins, acting as federated digital twins, and the user experience is at the end of this loop, where the user can see the output of the twin. In terms of sensors, as you can see, in Iliad, we have a series of sensors. We move from the low-cost sensors because we need a lot of systems like those. So we are testing for the first time, I think, a lot of low-cost sensors. We have also very expensive systems, so we range in terms of price from $100, let's say, to 100,000. So it's a very big range. LiDARs, echo sounders, drifters, microplastic sensors, drones, and gliders. All these are going to be shown to you right now. And the first low-cost system that we use in Iliad is this hydromast system. It is a system which was developed in the framework of another Horizon project called Laximi. And the interesting thing about it is that in Laximi, this sensor was measuring with an auto-recording system. What we are trying to do in Iliad is to connect it with a modem and to be able to transfer the data to a local server so that we have real-time measurements as the system is on the bottom of the sea. This system, the basic idea is that, as you can see, there is a rod over here which has the capacity really to move according to the strength of the current and the direction of the current, and there is a compass which measures exactly which way this rod bends, and it gives us an understanding of the magnitude of the velocity and also the direction. So in parallel, it has also wave, a pressure sensor, so it measures waves, not only currents. And it is one of the systems that I think can be extensively used in digital twins, since it has a cost of €100. As you can see here, there is, for each sensor we use in Iliad, there is this template where we define the specifications, mechanical, electrical, the connectivity, how the system will be able to emit the data or to take any directions from the user, and then the maintenance and the collection of the data, what sort of data sets are produced, etc. This is another system. It's called the microplastic sensor. It has been developed by Iliad. It uses 2 beams of laser. So based on the output of these laser beams, we are able to identify a series of different particles. As you can see, plastic particles, which are over here. And then we have cigarette filters, metals, wood, and leaves. Anything inorganic can be measured using this technology. Again, this is a sensor which was developed in a project some years back called Common Sense. Then it was also updated and upgraded in Odyssea, and now we again try to upgrade the system, integrating the capacity really to transfer real-time the data to the local system. We have the drones. The drones are detecting external damages on wind turbines. Then we have also the capacity of the drones with a camera to detect jellyfish swarms. So this again is something that gives us an understanding on how to utilize these vehicles and these systems in the framework of a digital twin. We don't have data as numbers here. We have data as images and videos. And of course, we need the specially written algorithms to analyze all these images and video recordings, so that we are able to identify the presence, the occurrence of jellyfish or any external damage at on the wind turbines. Another sensor, which of course is very expensive, is the Alcea Mars glider. It has been tested in several areas, in Thracian Sea, in the Black Sea for the first time, and then in the Alboran Sea in Morocco. In Iliad, we have 2 payloads. One is the anoxia payload, where we have sensors like CTD, chlorophyll, turbidity, CDOM, sensors, dissolved oxygen, of course, methane, hydrogen sulfide, and CO2. This was the payload that we worked for the first time in the Black Sea. And then we have the ecological payload, the CTD, the chlorophyll, the turbidity, and the CDOM. And for the first time, we tested a camera, UPV6 camera, which has the capacity to record the zooplankton abundance and diversity. So for the first time, we in Iliad really, and this is an analysis that we have completed for the Thracian Sea, we have observed the zooplankton diversity and the abundance in the Thracian Sea at various levels. This glider can go up to 1,000 meters depth, and over its movement, it collects data through these sensors. Another system, which again is a low-cost system, is the sensors that we have by Ilvo. These sensors are deployed, are installed on fishing vessels, and you can see they are very standardized, the GPS of the vessel, another system which measures the towing force, which is accelerometer, the landing sensor, and the fuel consumption. And all these data are accumulated to this microchip, and from there they are transferred to the cloud server, and from there we have the analysis and the real-time or near real-time understanding of what happens in terms of fisheries in the North Sea. Another system that my colleague Marco Oliveira will present to you in a moment are the Wavy drifters. They are again considered as low cost. The cost, I think, is of the order of €1,000. So it gives us an understanding of the currents in a Lagrangian sense. All the other meters are located in one position, so they measure the currents as in a Eulerian sense. Here, the drifter is moving passively with the currents, and it moves also up and down with the waves. So we have two types of measurements. One, understanding the strength of the currents and the dispersion of particles as a result of these velocities, and the other is the understanding the vertical movement of the sensor, so having an indirectly recording the waves and the changes in sea level. The ILVO sensors, here you can see the whole system, how the ILVO sensors collect all the data, what sort of sensors. For example, we have CTDs or turbidity sensors, weather stations. We have the towing force sensors, and all these give, which of course are useful in order to understand when the fishing vessel is fishing. Another system which is extremely interesting is that one from Doctech. This is a company from Israel which collects data from tugboats. You see that they use the GPS, the radar, the wind, and the temperature sensor, the echo sounder, in order to understand the bathymetry of a port. So they collect all this data and they enrich the databases, and using models, they are able really to provide high resolution maps of the seabed of a port area. So this is extremely important, especially in ports which are located very close to the river mouths, where we have siltation effects and the bathymetry changes on a day-to-day basis. Another system is here. We have the wave energy converters at Jaffa port, and we have the deployment of hydromasts at the bottom of the sea. In this wave energy converter, now they have also deployed two other wave riders. So they are testing the capacity of hydromasts to record effectively and efficiently and accurately the waves. So there is a calibration taking place, especially, which is extremely important in case of these low-cost systems. Here we move to high-cost systems like buoys from the HCMR Poseidon system, which is deployed in Cretan Sea, a series of meteorological stations in Crete and all over the land around Crete, but also Sentinel-1 images, data from Copernicus, data from NOAA, and bathymetric data from GEPCO. All these data are integrated in the digital twin for the Cretan Sea. And we also moved to another system in Norway, in the North Sea, where they have deployed this very big buoy, as you can see, with a benthic observatory. This is a very highly precise and accurate set of sensors where all the data are collected in a data logger. And as you can see, they have ADCPs for the measurement of currents and waves. Currents are measured at different levels through these echo sounders. Then we have the waves, which are measured also by the ADCP. Then they have the CTDs, which is recording the temperature, the salinity, and the pressure at the benthic station. The weather stations and the seal cameras on the buoy, and the microplastic sensor. The microplastic sensor is the one that I showed you earlier, but now it has been integrated in the observatory, and the data are also validated by this SealCam. So based on the recordings of the particles which are observed by the camera, we have a validation, indirect validation of the microplastic sensor. In Israel, we have also this series of sensors. We have drones which fly with LiDARs, and they are able really to give us a highly accurate bathymetry of the coastal zone. Then we have 3D seascape modeling of the habitat of certain species. And then we have this underwater camera which targets fish and is able really through machine learning algorithms to understand the fish species and the diversity and abundance and distribution of species in the habitat. So here we move to my area in Thracian Sea, where we have deployed all these sensors. As you can see, we record the waves with these two wave riders at two locations in Alexandroupolis Gulf. This is a location where we already have a newly deployed LNG terminal. Here we have some surface sensors, which this system is deployed near a mussel farm. Here we have these buoys, 4 buoys we have now, which collect data from ADCPs. They collect data on the currents, the waves, bottom temperature, and a series of water quality parameters. I will show you later on. This is the lander, which is deployed over here, where we have an oil rig from Energean Oil and Gas. And then we have the movement of the glider on a seasonal basis along the deepest part of the Thracian Sea, which is this North Aegean trough. So I think it's time now to show you a small, very short movie. This is the interface that we have developed in the framework of Iliad. As you can see, it's bilingual. The user can click on any of the sensors and collect data directly from the sensors. So the user selects, for example, that particular sensor. And as you can see, we can retrieve the data from the database, from the server. These are data on significant wave height. As you can see, we can zoom in at certain periods. We can get statistic for this particular period, the statistics, the minimum, the average, a standard deviation. We can move in this window in time. We can click on these lines and get the data in different format or get the diagram. And we can also zoom out and take the results of the numerical models. For example, over there, we have a series of tools for the currents, for the waves, the winds, and the sea grasses. And you can also change the background, which is the background that you would like to see. So for the currents, you see the output of the numerical models. This is the hydrodynamic model for Thracian Sea, and you can slide the slider in order to move in time your animation. Then you can also visualize the waves as they are produced by the numerical models. These models are forced by the Copernicus data and ECMWF. These are the forecasts of the winds. And then we have the distribution of seagrass in the area according to EMODNet. So as you can see, we are using all these databases that Bente explained earlier. And now we run an experimental oil spill model. This is called OpenDrift, is an open source model. And the interesting here is that you can run the model in real-time mode, and you can get the results. And of course, you can alarm the authorities. And in the next step, we are changing this to give us the opportunity also to add any mitigation measures. For example, we will also add the capacity for boomers, which will, of course, minimize the dispersion and the advection of the oil spill. So this is my presentation. Oops. Thank you very much.
Thank you so much, Georgios. It looks very impressive with all these sensors. There's a great variety. I think that became clear that you have some of the instrument sensors are very expensive, and some of them are less expensive. And so we have this whole range and also different resolutions, etc. So thank you very much, Georgios. If people have questions here and want to comment, please do so before we are looking closer on one of the sensors, and Marco will do that for us. If you raise your hand or you have a comment, please let me know. While you are thinking about that, I want to share the results of the poll, because while you were speaking, Georgios, I was asking the audience here if they are using sensors. You know, have we some sensor user here? And indeed, we do have. You see the results here. There are many that are both operating and using data from the sensors. We have some that are using sensors, and then the rest want to learn. So this is, thank you very much for participating in the poll. You know, I like that. And it's just some information about who we are and what we are doing. So thank you very much. So we have the right audience here. Now we are moving on to the next speaker, to the Wavy drifters. And in order to explain that to us, we have Marco Oliveira from Inestec in Portugal. And he's a senior researcher and leading the Human-Centered Computing and Information Center. And he has also an expertise in the Wavy drifters. So Marco, the floor is yours.
Sorry, somehow lost the mic. Okay, I have sound now. Yes, you can hear me.
Yeah.
So I will try to be short on the presentation. So we do need make informed decisions. We do need the data, especially on the nearshore areas, and I will focus this presentation and the Wavy drifters on a specific set of Wavy drifters that we not in Inestec, because we didn't develop the hardware, we developed the software, but we used in previous projects, and we are bringing them to Iliad also. So the focus will be more on the nearshore areas, although I will present the other drifters that we have developed in the previous projects. So to collect this data, it's not easy in nearshore areas, because there are a set of challenges in these areas due to the nature, storms, wrecks, several structures that exist, even the seasonal changes of the weather and the sea conditions. Nevertheless, these areas are really important due to several factors. And what we have at the moment to collect this data is a set of mechanisms that requires manual sampling, creating the infrastructures to collect the data. Using robots is not easy. It may be dangerous even. And with the remote sensing, we don't have much visibility on the data that's collected due to the specific water dynamics, the foam, the waves, and so on. So this is the basis to the design of these small drifters. Within this family of drifters, we have designed in previous projects, the project below. I will have the link for it throughout the presentation, and also in the end on the last slide, you can see the facts for the project. So within Project NLOA, we started developing two small drifters, two round drifters. One for using offshore in the ocean, open ocean, That's the bigger one. It connects to our systems through satellite to the CLS constellation. And we have another one, a smaller one, somehow a little bit bigger than one hand, that connects with GSM communications, and that's the one that we will use in Iliad. In a recent project, we also started to work on 3 other sensors. In this case, it's a little bit different. It's not a brown, it's a cylinder, and this allows the company, or the Ocean Scan company, to change the payload. And we have tested this with 3 different payloads, with an echo sounder, a listener, so with an hydrophone attached to it, and with a video camera. So this is currently the family of Wavy drifters that is available, although the 3 on the right are yet on prototype stage. So just for you to take a sense on the sizes of the drifters, on the left image we have a little one, so it's somehow a little bit bigger than the one hand. And on the right you can see 3 different sizes of the drifters. The leftmost one is the ocean one, so it's the one that has capacity for at least 3-4 months of battery and communication through satellite. This is just to show you the capabilities of the Wavy drifter, the littoral ones. They have a small exposure to wind, so they drift with the currents. They are easy to collect also. You can do it with a net or with a small net. It's the best way that we got to catch them. And this, as you can see in the animation, they drift with the currents. They are perfect to showcase, for example, the rip currents in citizen science projects, where we want the summer people that is on the beach to understand the dynamics of the rip currents and to showcase this. So this is one of the areas that we use the drifters for, is to create citizen awareness about the currents near the seashore. Going into the system that collects this data. So this data is always being sent in near real time to a central system. We updated the system during this last project of Wavy, where we started collecting also multimedia data from these 3 new sensors that we tested with. I will show also a small video afterwards. So we do have one part of the system that is collecting the data in real time, whether it comes from satellite or from GSM communications. We have some processing done here, so that in the output the data is already harmonized to be ingested in the software. This is our backend. We have capabilities to pre-process the data, and for example, Georgios said that we in these drifters we do have, in the little ones, we do have also the vertical movement. For example, one of the processing that we do within this system is to calculate the wave parameters after collecting the data. So this is not done on the drifter itself. It's done afterwards in a processing service. This data can then be shared also in real time with other software, with the specific software for the digital twin. and can be stored and processed and analyzed and correct in our system that I will show briefly in a minute. In terms of the system itself, we do have one software that we call Wavy operation software that allows us to manage the deployments and the campaigns, the data sets that are collected after each campaign also can be stored here. We have mobile applications. One, for example, that is the Wavy fundamentals. That is a small set of these applications, but on your mobile phone. We implement Wave citizen awareness application. This is done automatically to once you define a campaign as public. This allows us to easily start a new citizen awareness campaign from the software system. And we do have one application that allows us to help the recovery of the drifters once they are deployed in the ocean. This is just an application that defines which drifters are being used in each of the campaigns and where they are located from the user's point of view. I will jump now to the Wavy software, just to give you a glimpse of what we are talking about. Maybe let me just get here, pass it through here. And I think I am on time. So within the software, you can prepare a campaign. In this case, is the campaign from La Palma in the time that we had the volcano eruption. Here on the website for the deployment, for the preparation of the campaign, you can, if you are using for example, the ocean drifters, you can look into the status of the satellites and see when you will have communication. So when you expect to receive the data in real time or not, so that you can plan also the campaign and the location of it. You can, just jump to one. You can say identify which of the drifters you will be used in this campaign. And once you define the drifters, you can set up the deployments for each of the droppings of the sensors that you will have. This is a somehow important step, because from the information that you define associated with the deployment, you will then generate automatically the data sets for each of the drifters that are used in your campaign. These data sets can then be curated by the user and can be shared publicly in a catalog, in a public catalog, such as the Next.use, and I will jump here now, such as Next.use catalog, sorry, this one. And here in the Next.use catalog, you have all the public data that was produced during the MLOA project, but just by searching here MLOA, for example, and you can have access to this data and see how it is produced. There is an intermediary catalog. This was developed by Deimos, also a partner in Iliad project, where you can also collect the data that was produced. From these campaigns, you can also navigate the campaigns. So this is similar to other softwares. You can go through, and doing steps of 10 minutes. You can go through the drifting, the sensors. This is for a set of littorals in an example of a campaign. And for example, I will put on steps of 2 hours now. This was during the campaign that we saw in the setup on the system, and this was from the campaign from the La Palma. So you can see that on this case, from time to time you will receive more data because we had different messages arriving real time from the drifters. I will just jump a little bit more here. Just to give you a glimpse of the flow of the data. So this is somehow 3 to 4 months of data in this campaign. So the data is available in the Next.use catalog, so you can have access to that data. So this is the same as we saw before. These are links. I think you will have access also to the presentation. Afterwards, you can search for data in the data catalog for this campaign. And this is a small video of deployment of the drifters during the Wavy project, the drifters that have the payloads for Imager, Listener, and Echo Sounder. So the ones that we will use are round, but it's similar to the process. And the collection of the drifters afterwards. And thank you. I think it's all.
Thank you very much, Marco. I have to say, as a nature-loving gadget geek, I'm, itching after playing with those drifters in the ocean, and it seems to be, something useful you can do.
And sorry, I tried to be on time because I was asked to have some time afterwards for questions. So due to the time, I tried.
No. It's all good. Very interesting. Thank you both. And do we have some questions in the chat? Let me see if I have some questions. No, raise your hand. We are so few here. It should be possible just to raise your hand and ask questions or make some comments. Anybody with experiences you want to share on using sensors? What are some of the challenges? No questions. Well, while you are are you planning to ask a question, Yori? With turning on your camera.
Yes, thank you. Well, good morning, and thank you both for your presentations. Very impressive results you have there. I was planning to ask Georgios just about the technology that they use for the visualization of the measurements. I just wanted to know which platform is being used there to.
We use, it's written by us. It is not, we extended, we started initially with Leaflet. I don't know if you know Leaflet. And then we extended it. It is written in Python and JavaScript, and it's developed in-house. The only thing is that I wanted to say and to comment here is that, all this work with the sensors is a work with a lot of risk. It's very common in the sea to lose your sensor or to have an accident or to have a difficulty. For example, one of the systems now that we have in this particular period is not communicating with us for the last 24 hours. So we have to go to the sea anytime, any hour, to see what is happening, why we have lost communication. Also in the summer here, this is a very touristic place, and many boat owners approach the sensors, approach the buoys. They try to see what is inside. They try to open the data logger. So all this really creates a lot of problems and risks for us. Imagine if you have a review and just before that you have an incident like that. But other than that is, it's the whole system is a very complex system. The issue is that in digital twin cases, we need to have the data as quickly as possible. So we need really to be real time or near real time at least. And this is the challenge. This is why even with the low-cost systems, we tried really to upgrade them and give them the opportunity really to transmit data in real-time mode. If we are able really to validate the data of these sensors, we will have made a significant step, I think, for oceanography, for the digital twins, because in the digital twin environment, from my point of view at least, you need a lot of sensors, a lot of data points, so that we are able, and also you need a lot of sensors that can be easily and without significant cost be substituted in case of malfunction. I see there is something I said and someone wants to.
Yeah, Edmund.
Let me just compliment that. That's one of the bases also for the development of these littoral wavy drifters is to be easily deployed on the ocean. These are meant to be collected every day, so these are meant to be one-day campaigns on the little ones. In the case of the ocean, you can let them drift by their own throughout months. Okay, those are main differences here.
Thank you. I give the floor now to you, Edmund. You also raised your hand. We can't hear you, Edmund. It looks maybe like you have some issues with your microphone, because I cannot see that you are muted even, and we don't hear you. We don't hear you. Maybe you can.
If you want the chat to write it in the chat.
Yeah, write in the chat, Edmund, and then we can. Yeah, it's an issue there. So then we are just hearing noise. Let me see.
Yes, thank you for giving me the floor. So, hello?
Hello, we hear you now.
Hello?
Hello, Edmund. No. Okay. While Edmund is sorting out his issue with the sound, we ask then, well,
Bente, there is a question from Babis in the chat.
Yes.
Will the sensor data be made available? In the case of the data that is collected with the wave drifters, it depends on the data owner, in this case the pilots, to provide the data openly in the catalog. We are setting up the connection of the possibility of extending what we did in previous projects to connect the data to the catalog, to the data catalog of Iliad. So this is being prepared, and it depends on the pilots to share the data that they collect within the campaigns. Of course, they have the possibility of curating the data before deploying it to the catalog.
Marco,
Yes, Georges.
In terms of satellite communication, is this something that is already made available? Is it something that we have to take care of? Is
The
it so?
satellite communication will not be available in our sensors in satellite in Iliad, because we will not use the Wavy ocean drifters.
Okay.
The GSM communication, that's the one that we use on the littoral drifters, it is being taken care of. So some part of it will be if you don't expend too much in communication, it's dealt with. We will have to talk that with the pilots also. Yes.
Yeah. So I noticed,
but we do have a platform for the data communication.
Okay.
yes, I noticed, Marco, concerning the satellite. You show that you could get information about the satellite connectivity.
Yes.
And that's for the ocean drifters, right?
That's
So,
for the ocean drifters. Yes.
yeah.
That's
yeah.
implemented in the platform, but it's not. It will not be available in Iliad, because we will not use the ocean drifters.
But that's a capacity for.
Yes, that's a capacity that we have in the system.
And what we can do in Iliad then is to demonstrate, to set up a system where we are connecting those littoral drifters and feed that into the system with near real-time data.
Yes.
On a campaign basis. And some countries have very good GSM coverage and others not. So I think, yeah, so we are looking to, I don't know the situation in your part of the Mediterranean, Georgios, but in Norway in general, the GSM in particularly in the Oslo fjord, where we are planning to, and in Trondheim also, the Trondheim fjord is very good connectivity. So stable.
Yeah, here in Greece as well.
Yeah, it is. Yeah.
At
So
least
this is good.
close to the shore.
Yeah, close to the shore. Yeah. Okay, we are. I don't know. We might come back to this data sharing, but I want to give the floor to the audience here. Sadra, you were asking for the floor. Hello, nice to see you again.
Hello.
Hi.
Thank you very much for the nice presentation. I have a really short question. I mainly work with the sensor data from in the transport sector, in the urban planning sector, and the presentation that Marco provided. I have one question. How much is the operation cost? Not just the sensor, the time that you show the data is collected. Can you provide a little bit brief information about the cost of operation, please?
What do you mean by the cost of operation in this case? The cost of the access to the system, the cost of the data share, the data collection?
Yes, the data collection part.
Okay. I cannot say the cost of the cost of communication through satellite, because I don't have it by heart. I do know what I know is that we have been talking about this the last few months with the company, with CLES, but the costs that we have are within the consortium of the project, so I cannot talk about this outside of the consortium. Regarding the communication through GSM, we are using a global actor on the GSM, and I can tell you that if you have the drifters connected all the time, that it doesn't happen, but all the time throughout 2 months, if you have 20 drifters, I think it will end up in a cost around 500 euros. Okay, that's the amount.
Thanks a lot. I just need the scale. Thank you very much.
Okay.
Thank you, Sadra. Thank you, Marco. So, Edmond, I'm not sure. We have some issues with the sound from you. Can you give it a try? And if it's too noisy and we cannot really hear you, can you please then ask your questions in the chat, and then we can answer it? Okay. Give it a try now.
Okay, okay. Hello?
Hello.
Hello. So thank you very much for giving me the floor. So I'm from Madagascar, and I'm very happy to be part of us during this meeting. Thank you for the presentations, which are very important and rich in informations. My question is about is there environmental impact uh, using those several sensors, especially for the species which live in the ocean ecosystem. So thank you very much.
Yes, interesting question. Georgios, can you give it a try first, and then you, Marco?
Sometimes there are concerns about the echo-sounders because the echo-sounder emits sound, and perhaps in some frequencies this annoy some species. We haven't really, I haven't seen any report, but recently I tried to deploy one system in a protected area, and the organization there responsible for the management of the protected area did not allow me because they wouldn't really like to see a contamination of the area with echo sounding. The other issue perhaps has to do with some leakages from the batteries in case you have, because these sensors are deployed for quite long periods. And they are serviced every 6 months. Most of the time, I send divers every 6 months for the maintenance. There is a case when we have the leakage of battery fluids or some oils that can be, of course, dispersed in the ecosystem. Other than that, I don't really think there is any other case that we have any impact of the sensors on the environment.
Thank you. Yeah, thank you. And Marco?
I must say that that was a discussion also in the other project where we developed the drifters. That's why we made those drifters to be collected, and they are completely sealed. So there is also the possibility of leakage if it goes into rocks and something indeed breaks. It might happen, but as they were created to be collected, the literal ones at the end of the day. So in principle, that will have no impact. In fact, the ocean ones, I must say that was not really evaluated as it is. But we found no issues at the time, so I cannot say any much more about that.
Yeah, thank you. Thank you. It was a very interesting question, and of course something
Yes.
that we need to think about. So thank you, Edmund. Did you raise your hand again? Is it a new question, a follow-up question, or was it a legacy? Edmund?
No.
Oh, okay. Thank you. Any other questions and or comments? No, I think, well, I have one question, and that to you, Georgios, because your pilot there in the oil spill, you are using multiple sensors, different types of sensors. How is the interoperability and harmonization of this different sensor data? It's a complicated system. How do you make this a meaningful combination of these data? How can we do analytics on it? I saw that you were showing, individual data sets from the different sensors, but are you also combining it in another way? Well, yeah. So harmonization and interoperability between, you know, of all these different types of sensors that you have in your twin.
This is for me, Bente, sorry.
Yes, it was for you.
For the interoperability, firstly, let me say that all the sensors we deploy in DOOTH are openly available for the Copernicus harvesting. So we transfer the data on a daily basis 3 times per day, if I remember well, through the in situ TAC. There is a service of Copernicus, which is run by the HCMR, the Hellenic Marine Center of Research. And they have an algorithm which we provide them the URL, in which particular area the server the data are located, and what sort of format of the data, which column represents which parameter, etc. And based on this, they enter the server 3 times a day and they harvest the data. This is extremely important for us because we have seen that the model results, the forecasting model results of Copernicus have been considerably improved for Thracian Sea. So now we have very reliable forecasts for the waves, for the currents, for the water quality as a result of the deployment of these sensors, because the data are assimilated in the Copernicus model. And as the Copernicus model results have been improved, our boundary conditions for the localized high resolution models that we run for case per case, for example, in the case now of the Iliad, we run the oil spill model, have been really improved and give us better understanding of what is happening. So the uncertainty is limited. So I think from my point of view, this is the proper policy to have everything open. As you can see, these data are open. Anybody can download them. Anybody can use them. They are in standardized format anyway. They can give them, we provide them in CSV or in Excel. We can also translate them easily in HCDF or anything else. But as I said, they are integrated in the in situ TAC of Copernicus, so interoperability is achieved this way.
Okay, so there's 2 points to that. So first of all, you are actually setting up this whole system to actually be interoperable with the Copernicus. So that's from the get-go. So you are actually designing the whole system you have is designed to do that. So that's one thing. The other thing I noticed, you just gave us a very good argument, Georgios, why the individual data providers will benefit from sharing the data, because the overall then met-ocean model will be improved, that you again can use, right? So it's sort of a iterative process.
Exactly.
And then the more of the individual data providers who are doing that, everybody benefits. So yeah, that's a good argument for data sharing, actually. Okay. I don't see any more questions in the chat. We are 11 minutes past the hour. I think we can call it a day. If you don't, maybe you have some additional comments, speakers, Marco and Georgios, before we close the webinar.
We are available, of course, for any of the participants in the hackathon, for any question, for any advice in relation to the sensors, in relation to the data analysis and visualization issues, anything which was presented today.
Yes, thank you for reminding me, because actually all of this will be available for you in the hackathon. So you are basically inviting people to play with the sensors that you have control over, right, Georgios? And you are ready to support those who want to do that.
Yes, of course. Or any other ideas that can use this data for any other services.
Excellent. Yes, perfect. So this is your opportunity to really benefit from state-of-the-art sensors and expertise on high level. Marco, do you have any final words as well?
No, just that we expect to be able to use also the sensors in the scope of the hackathon, right? So I hope that you will have the opportunity also to play with them and to create some citizen campaigns also in the scope of the hackathon and collect the data and use them in your own projects. Most of it to validate also the outputs of the models on the currents, for example.
Yes. Okay. So this is an opportunity, I think, an offer you cannot refuse, I would say, to do this summer. So the hackathon is going on now. If you haven't really found your team yet, you have registered and you haven't found your team, please do that. Let us know, and then communicate that you would like to work on either of these sensors and invest a little bit of time on that. Let us know. We are all ears still. We are very flexible. And the hackathon is going on until the 11th and the 12th of September. So there's lots of time to spend on these sensors during the summer, and with a result by in September. Okay. I thank you again very much, both the speakers and for some very interesting questions and comments here. So until the next time, you follow us here on Iliad. We will both in social media and follow on the webpage. Take a look at the hackathon webpage, because that's where the recording and slides from all of the webinars will be made available there. So just go there, keep yourself updated via the social media and the webpage, and then of course you will, if you have signed up for the hackathon, you will get email communications as well. So with that, thank you very much, and until the next time, and have a lovely weekend.
Thank you.
Thank you.
Bye.